Okay, this is part 2 of the simple harmonic motion, meaning like this is the solution to the problems. You have all these solutions on your answer key, but sometimes I try to do different approaches to solving these problems. So on page 2, where you have these graphs, we probably talked about this in class, or you have done a lab prior to the lesson, and you figure out that if you look at the position time versus the velocity time, you're going to see that there is a shift of a quarter of a cycle. Okay, and if you look at the position, which is all the way on top, and the acceleration, which is all the way at the bottom, you're going to see there is a shift of pi, or basically half a period. In other words, when the position is at maximum, the acceleration is at minimum. I mean, it's still at maximum, but negative. Okay, so it's on the other side. So the acceleration time graph and the position time graph are always flipped. Okay, the values on the y-axis here are not the same. Okay, and I'm going to show you what those values are. If you haven't, I think we're going to do that in class. So we've done that in class already, or we're going to do it. Okay, the rest is basically just a bunch of definitions. So if I'm looking at this mass hanging here, okay, equilibrium position is right there. Okay, so I'm going to think of that position as an unstretched position. So anything that away from that position, it's either stretched or compressed. So if I pull this spring to here, right, and I let it go, it kind of comes up to here. So I'm going to call this position negative A. I'm going to call this positive A. And this is 0. So you can do it the other way. You can put this as negative A and positive A. That's how I'm going to do it in class this year. Okay? And I do it every year like that. Okay. Okay, so that's the definition of equilibrium position. You can read that. A restoring force is basically a force that wants to bring you back to your equilibrium. So let's just look at this object, this mass, when it's oscillating, and when it's at position A, the force is directed towards equilibrium, because when it's here, it wants to go back to here, right? So whenever it's here, it always wants to go back to this position. When it's past here, it always wants to go back towards that position. So that's why we call it a restoring force, because it always wants to restore you back towards the equilibrium position. So this force is always directed towards the origin. So now this is a spring on a flat surface, so that can oscillate around this equilibrium position. Okay, the amplitude, just like you learned in your math class, trig class, is basically, just find some markers here. Okay, it's just the maximum displacement, okay, away from equilibrium. So in this case here, the maximum displacement is that distance between my two fingers. And it should oscillate around that, but because there is damping, which is friction basically, it eventually slows down and does this funky stuff. Okay. So that's what amplitude is. And with amplitude, we just look at the positive value of of A. We don't look at the opposite side. Okay. So this is basically going to oscillate between these 2 points here, and basically this is your amplitude. So in this case, based on this picture, they're looking at right as positive. Okay, the period is basically how long it takes to do a cycle. Okay, and you learn in your math class that whenever you do trig functions, you always break your period into quarters, because the important stuff, the interesting stuff happens at the quarters, right? So if I pull this here and I let it go, when it reaches here, that's a quarter of a cycle, another quarter, 3 quarters, and back to the period. Now, the period of a pendulum, maybe I'll prove this in another video, or maybe you can just accept it. It's 2 pi square root of m over k. Okay? M being the mass that's hanging on it, and k being the constant of this spring here. So let's see if this actually makes some sense. If I hang a heavier mass on here, I have Mr. Hughes and Mr. McQuaid here watching me, so I don't know. They're trying to kind of like make me smile or whatever, but I'm not going to smile.
I do not smile.
All right, I do not smile. All right. So if I have a heavier mass, okay, whether it's heavier or lighter, the amplitude, okay, how much I pull it from the equilibrium does not affect its period. And we can try that in class and take some measurements. Now let's look at the relationship between the mass and the period. If I have a heavy mass, more mass means more inertia, which means it's going to take a longer time to get down there. It's going to take a longer time to go back. So in other words, it's more inertia means more resistance to change, right? So if it's heavy, it's going to resist more, which means it's going to take longer, okay? For the spring constant, if you take a spring with a high spring constant, a high K, in other words, it's pretty stiff, right? So when you stretch it, its reaction is quick. It wants to go back quickly because of that stiffness, right? So if K is high, right, the period is low because it reacts much quicker than a spring with a low K. So I hope that explains conceptually why the T is directly proportional to mass, or the square root of the mass, and inversely proportional to the square root of the spring constant. Okay. The frequency is just basically, so the period is how long it takes to do one cycle or one vibration. The frequency is basically how many vibrations you do per second. So it's just the reciprocal of period. And the units for frequency is in hertz, and the period, as you can see, that it's in seconds. Okay, the next thing I'm going to talk about is this angular frequency. Sometimes we call it omega. It's basically 2 pi over t. So I'm going to write the formulas here. So t equals 2 pi square root of m over k. And the frequency is 1 over 2 pi square root of k over m. You just flip that period. Okay. Okay. These are the equations that we came up with from the graphs from the lab. So this is, I can write this as A cosine omega t, right? And I'm either going to show you in class, or I've already shown you that where these formulas come from. So for people who do calculus, this is pretty straightforward. But we're going to try to do this by doing conservation of energy in class. Maybe conservation of energy and Newton's second law, combination of those two. Okay. This stuff we should have talked about already in class. So let's take a look at it quickly. Okay. When you're away from equilibrium, whether compressed or stretched, the force is always towards the equilibrium. So anywhere in here, your force is going to be in that direction because the spring wants to push back and get back to the equilibrium. Here, the force has to be in that direction, which means the acceleration is also in that direction because the direction of the force and the acceleration is the same. Now, you can see that the acceleration is less as you get closer to the equilibrium position. And the reason for that is because the force is less. The amount of compression or stretch is less. And we know that that force is directly proportional to the displacement. In other words, the amount of stretch or compression. Okay. When we are here, our speed is 0. Okay? And as we go in towards the equilibrium, we're picking up speed. And the reason for that, because whatever loss you lose in the elastic potential energy gets changed to kinetic energy. So as you go in towards the middle equilibrium position, your velocity should be increasing, and it will reach its maximum speed at the middle. That's just conservation of energy. Because in the middle here, you pretty much have no elastic potential energy, so all that energy you had when at the outside there became kinetic, so which means maximum speed. And as you go in this direction, you compress in the spring, which means now you have more elastic potential energy, which means you're losing some speed. You're getting that elastic potential energy at the expense of kinetic energy. And you get to the other end, you stop and you turn around and the cycle repeats. Okay. And here you can see that if you are in this position here, your displacement is here. Okay. If you are here, your displacement is there. You can see that the acceleration and displacement are always opposite. So that's what the graph showed us before. And this is just the a bar chart representation for what I just talked about in terms of energy. Okay, so let's look at this problem. So that was a quick summary of simple harmonic motion. So for this one here, this is periodic, but it's not simple harmonic motion. In order for it to be simple harmonic motion, the restoring force has to be proportional to the displacement, which is not the case here. Now, why is the period 2.8? Well, you can figure out how long it takes to drop 10 meters. So you can just do h is half gt squared. So this is going to be 10. This is going to be another 10. So t is going to be radical 2, okay, which is about 1.4. So if you double that, you get your period, because period is when it comes back to the same place you dropped it from. Now, this problem here, I'm going to try to do differently than the way you have this in the answer key. At which point or points is the acceleration positive? Well, the acceleration is positive when the displacement is negative, right? So that should be at point D and E. Okay, and that's the justification, what I just talked about now. Okay, so I don't want to scroll here, so let's take a look. And F also, I missed F. F is here too. So the displacement is, or the position is negative in there, so which means the acceleration has to be positive. At which point or points does the car have zero velocity but non-zero net force? Now, if you recall from kinematics, you can get the velocity from a position time graph by doing the slope. So the slope here is 0, and the slope down here is 0. So the answer should be A and E. Okay? And you can also think of it like, well, at this moment here, it has to change direction. It was going in the positive direction. Now it started to go in the negative direction because the position is dropping. So we're using the old kinematics stuff. At which point or points is the net force equal to 0? Well, the net force is equal to 0 when the displacement is 0. In other words, there is no stretch, there is no compression. So that's basically at C and G. Okay? And I'm not writing down the explanations, but I'm talking about them, so you can take notes on of that. At which point or points are the acceleration, velocity, and displacement all positive? Never. And the reason for that, because position and acceleration have to always be opposite. So there is no way that they're going to be on the same side of that graph. At which point is the acceleration non-zero and opposite in sign to the position? Well, it's going to be A, B, D, E, F, and H. Okay? So for A and B, the acceleration would be negative, which is opposite to the displacement, which is positive, right? At which point or points is the velocity non-zero and opposite in sign to the acceleration? Let's take a look. Well, the velocity here is 0. The velocity here is just the slope of that tangent. That's negative, but the acceleration is also negative. Okay, so that's no good. Okay, the acceleration here will be 0, right? Yeah, okay. In here, the velocity is 0 because the slope of that tangent, the velocity is negative. That's the slope of that tangent. And the acceleration has to be on the other side. So D is an option. Okay? While E, the velocity is 0. At F, the velocity is positive, but so is the acceleration. The acceleration is going to be on the other side. So that's no good. And G, the acceleration is 0. At H, the velocity is positive. That's the slope of that tangent there. And the acceleration is negative down there, so it's D and H. Okay. Okay. Number 2. A particle oscillates up and down in simple harmonic motion. Its height is a function, so basically its position as a function of time is shown in the diagram. At what time does, time t, does the particle achieve its maximum positive acceleration? So you're going to get maximum positive acceleration when your displacement is maximum and negative. So that happens here. So the maximum positive acceleration will happen at 1 second. So that's your answer.